Okay, so good morning, students. Myself, Dr. Pooja Yadav, and we are studying operational amplifiers. And in operational amplifiers, we have already studied what are op amps and what are the parameters of op amp and what is the block diagram of op amp. These things we have already seen. Okay, so next is we have moved to what are op-amp applications. In op-amp applications, we have seen in the starting lectures, we have already seen operational amplifiers as an inverting and non-inverting. आप लोगों के माइक ऑन है, प्लीज स्विच ऑफ करो बेटा, म्यूट कर लो. भावना, प्लीज स्विच ऑफ योर माइक्स और म्यूट कर लो आप लोग सभी. Is it okay? Okay. So in the last lecture, we have already seen what is the application of op-amp as an integrator. In today's lecture, basically, we are going to see what is the application of op-amp as an differentiator. But before moving to op-amp as an differentiator, we will briefly look what is the op-amp as an integrator. This we have seen already in our last lecture, so I will not emphasis more on this, but our differentiator lecture is based upon this only. So if you have if you remember the things ki how we have designed an integrator by using the op amp, it will be helpful to us. So we will just look at the integrator, op amp as an integrator. This is the first picture of an electronic circuit, how the integrator will look like. We will have a power supply, and then there is a circuitry which we have to define ki what will be the circuit for an integrator. So here we have seen that we can define the integrator by a formula by looking at this circuit, that V out is equal to a constant integration of VI dt. Whatever we will give to this circuit, at the output we will need, or we need to have the integration of that input voltage from the circuit. This is the desired one. For this, we'll have to design a integrator. Okay. So we will just see how the actual circuit of an integrator will look like. So in our presentation, we'll have to design an integrator, and for this we will consider this circuit, that we are having a power supply, and if we'll connect a capacitor to that supply, we will have the integration of what is coming at the input terminal at the output point, and this will be given by the equation V out is equal to VC, that is equal to 1 upon C integration of I dt. What is continuously changing is nothing but the current. Okay, here capacitor value, that is value of C, is constant. So we have kept it outside, and we will, if we will take the integration of I dt, it will be giving the integrator circuit. Okay, so this is how we have designed the integrator. But here what we need is, we will need a output voltage. We have in the last circuit, we have integrated the current, but we are also in the need of output voltage. So what we will do, what we are going to modify in this circuit is, just have a look at this, that output voltage across this capacitor can be written as Q by C. You all know this equation, but dq by dt is equal to I. What is the value of current? That is nothing but dq by dt. Therefore, dq can be written as I into dt. If we put this value of q, it will be written as integration of I dt. So just put this value of q over in this equation number 1. So what we will get? We will get output voltage across the capacitor. So what is the output voltage across the capacitor? It is equal to integration of I by C into dt. Okay, from this equation we have got this. We have put this value in equation number 1, and finally we have got the voltage across the capacitor, that can be written as integration of I by C dt. Is it okay? So the integrator circuit, if we'll just modify the circuit, we are going to add a small resistance to the circuit, so that we will have the output voltage. And output voltage here, if we write VI by R, that is nothing but I. Okay, this is nothing but Ohm's law. You all know what is current. This is voltage divided by resistance. So if V out is small as compared to VR, so how we can write the equation as VI is equal to VR plus VO. V input, whatever we are giving at the input, it will be written as VR plus V out. Here we can write VR, we know VR is I into R. VR is nothing but voltage across the resistance. We can write it as current into resistance value plus V out, that is the output voltage. So if I is equal to C dVO by dt, if we write current in the equation of capacitor and the output voltage, we can write this equation as, put this value of I in the above equation. So what we will get? We have kept constant outside, that is RC dVO by dt plus V out. This is nothing but V input. So can we take the value of V out from here? We can calculate the output of VO if we know the value of RC, they are the constants, and if we know the input voltage. So this is how we are going to calculate the output voltage across the capacitor. Okay. So finally, if VR is very less than V out, okay, so we can write RC dVO by dt. This can be equal to VR. So how we will write? This equation will be modified as V out is equal to 1 upon RC integration of VI into dt. Finally, we need this equation. We need the integration of whatever is coming from the input, that is the input voltage. Okay, so this is the final equation for a integrator circuit. For good integration, we need this factor should be very less than 1. This is omega RC. It should be very much less than 1. So for the better results, what we do, this was the circuit. Here we were having a input source and a capacitor plus resistor combination, and in that we have designed the integrator. But if you want to have an application of op-amp as an integrator, how we will modify the circuit, we are going to see in this particular circuit diagram. So here we are having a op-amp. Here we are having non-inverting terminal and the inverting terminal, and at this point the op-amp is at virtual ground. You will have 0 volt at this point, that's why it is called as a virtual ground point. So how we are going to design an integrator by using op-amp, this is shown in this circuit. Okay, so this is the supply, this is the input resistance, and where we are going to connect our capacitor is at this point. At this point. Sorry. This is the circuit. Okay, this is the integrator. And here what we will do? We will just connect a capacitor over here. This is the input resistance. Okay, after the supply we have connected a series resistor, and the capacitor is connected in parallel with the circuit. So this is the output voltage. This can be written as V out is equal to minus of VC, because we are using a operational amplifier in inverting mode. Why in inverting mode? You all know, I have already told you op-amp as an inverting amplifier, because we have connected the input at the inverting terminal. That's why we will call this op-amp as an inverting amplifier. And for which application? For the integrator application. So we are going to design an integrator circuit by using this op-amp in inverting mode. So V out, if V out is equal to minus of VC, we can write V out in terms of C and R. This is minus of 1 by C integration of VI divided by R dt. Is it okay? This equation you all know. Now you can keep R at outside because it is also constant. So basically what we will get at the output end, we will get this circuit for the integrator application. So we can write VR is equal to VI. If this equation satisfies, so we can write finally VC is equal to VC 0 at this point plus 1 by C integration of IC TDT. Is it okay? So this is the final equation of what we get at the integrator output. So can we write V out is equal to minus of 1 by IC integration of VI TDT minus VC 0. So this is how the integrator will work for us. This is the equation, this is the final equation where we can have a integration of whatever we are giving at the input terminal. This is the input terminal. You can give a DC signal also, you can give a AC signal also. So we will just see if we are giving some AC signals to an integrator, what we will get at the output end. So this is how the circuit will look like. This is our practical circuit. Okay, and here if we give square wave to this circuit, what we will get at the output end, we will get a triangular wave. This is how the integration is done at the output end. If we give a square wave, we will get a triangular wave at the output. And for this, you can write the equation as Vs is equal to Vm sine of omega t, which is right, can be written as V out is equal to minus 1 upon RC. By looking at this circuit, it can be written as Vm sine of omega t dt, or if we take the constants out, Vm omega RC cos of omega t. And in this equation, you can write it as Vm omega RC sine of 90 degrees plus omega t. Why we will have minus sign over here? Because this is nothing but a op-amp or a operational amplifier in inverting mode. That's why whatever you will give at the input, it will be shifted by 90 degrees at the output end. So you can see from here that this square wave is starting from minus 3 volt, but at the output, when we are getting a triangular wave, it is starting from 0. Okay, so this is how the phase is shifted by 90 degrees. Okay, so you sorry, this is 180 degrees phase shift. So in inverting amplifier, whatever you give at the input end, at the output, you will get a phase shift of 180 degrees, that is out of phase. So this is how we used op-amp as an integrator in inverting mode. Now what is the topic? We will just have, this is the integrator portion, and what we need to design today is operational amplifier as a application of op-amp as a differentiator. So we will just have a look at what is a differentiator. Shravani, if your screen is on, you just switch it off. और बाकी है क्या? Mic भी on है तो इसको mute कर लो, please. Okay. So what is a differentiator? A differentiator is a circuit that performs the mathematical operation of differentiation. You know how we mathematically define the differentiation. So the function of differentiator is to provide an output voltage which is proportional to the rate of change of input voltage. Okay, here also whatever we will give at the input end, we need a differentiation of that input voltage at the output end. So how we are going to perform this differentiator circuit can be obtained by interchanging the resistance and capacitor C of the integrator. Just आपने जो इंटीग्रेटर का सर्किट देखा उसमें यदि हम कैपेसिटर और रेजिस्टेंस की वैल्यू चेंज कर दें तो हमें कौन सा सर्किट मिलेगा? ऑप एम्प एज एन differentiator. Okay, so we will just see how we will redesign the circuit. The input voltage V1 appears across the capacitor and its other end is at virtual ground. Okay, so we'll see the circuit, how the circuit of op-amp as a differentiator will look like. So this is how we can design a differentiator circuit by using an op-amp. It is just like, if you will see the circuit, we have interchanged the value of R and C. The resistor were here at the input end. We have removed that and we have placed the resistor in the feedback, and at the input we are giving the capacitor. So now the input is coming and the capacitor is connected in series with that input. Okay, so what we will get at the output, this is what we are going to see in this lecture. Okay, so first we will see what is a differentiator basically and what is inside the circuit of a differentiator in any electronic circuit. So this is nothing but a supply, and this is the circuit of differentiator. What it is doing for us, it is differentiating the input voltage. Okay, so that's why it is written as VDT of whatever we will have at the input terminal V1. Is it okay? This is called as differentiator. So how we are going to design by using an electronic component? Just connect a capacitor over here and you will have a differentiation of the input voltage. So how the current will be measured at this point? Across the capacitor you will have I is equal to C dV by dt. What is changing? It is the voltage. So we'll take differentiation of voltage multiplied with the value of capacitor. This will be the output current at this end. So what we will need? We don't need the current. We will need the output voltage. So what we are going to use? We are going to use a current to voltage converter by using an op-amp. So this is how we can design a differentiator. This is the differentiator circuit, and this is nothing but a operational amplifier. So how we are going to combine this? So this is the actual circuit of operational amplifier as a differentiator. Okay, so we have designed this circuit. How we have designed this circuit? We have connected the input, then we have connected a input capacitor, and at the feedback we have connected a resistance also over here. Okay, so this formula, this output voltage can be written as V out is equal to minus of I into R. Why this minus sign is there? Once again we are using the operational amplifier in inverting mode. In inverting mode means what? We have connected the input at the inverting terminal, and that's why at the output we will have a phase shift of 180 degrees. That's why this minus sign is there. So if you give plus 5 volt at the output, you will have minus 5 volt. Okay, this is how the inverting terminal works, and the output will be equal to minus of whatever you give at the input terminal depending upon the circuit. Is it okay? So here we will have VI is equal to VC. Okay, what is the capacitor voltage? It is nothing but whatever you will apply at the input. So this is written as VI. Okay, then what is current? What is the current? The current which is flowing from this point to this point. But always remember, at this terminal, you will have virtual ground. Why we have virtual ground and what is the voltage across the virtual ground? This we have already learned in our previous lecture. So we'll just have to remember that at this point we are having a virtual ground point, and no voltage or no current will flow from this, and you will have a 0 volt when you measure across this terminal. Is it okay? So this is I is equal to C dVi by dt. This is the input current. So what will be the output voltage? This is the for this we are concerned. So output voltage will be equal to minus of RC. This is the equation for this, minus of RC. This is the constant because value of R and C is going to be constant. What is changing is dVi by dt, integration, differentiation of voltage, that is dVi by dt. Vi is input voltage. So we will have as the output minus of RC dVi by dt. This is the differentiation of whatever input voltage we are giving at the input terminal. Okay, so this is the final output voltage. Once again we will have the same circuit. So what will happen to this circuit if you have I2 as I2? What is this I2? This is this point. This is considered at the current flowing from, this is a feedback resistance. Okay, so there will be I input and I2, that is the output current. So this is nothing but 0, because at this point you will have 0 volt minus V out divided by R. This is nothing but the Ohm's law. So what you will have at the I2 current, minus of V out by R. So if we can write this equation in the form of C dVi by dt, we will have in the place of current we have written C dVi by dt. It is equal to minus of V out by R. So we can write from this equation we have extracted what is V out. So V out can be written as minus of RC dVi by dt. Just break this equation and keep V out at this side. We will have V out is equal to minus of RC dVi by dt. What is this? This is the constant value. R is RC. They are constant. And at the output, what we will have? The differentiation of input voltage. Okay. So this is how we can have a differentiator by using a operational amplifier. And why we have? Just have a look at this equation. Once more, we are having minus of RC. Why this minus is there? Because we are using op-amp as an inverting amplifier. Why op-amp as an inverting amplifier? Because we have connected the circuit, we have mounted the circuit at the inverting terminal. Okay, this is how we are giving the input to the inverting terminal. That's why at the output, you will have a phase shift of 180 degrees. That's why we will have minus of RC dVi by dt. So is this equation very clear to you? This is op-amp in inverting mode and op-amp application of op-amp as a differentiator. So we will just have a look at the waves, how the waves will look like, what is the input if we'll give, if you are going to give a square wave. If you are going to give a square wave to this circuit, you are going to get spikes at the output terminal. If you are going to give a triangular wave to this circuit or to the circuit of a differentiator, you will have a rectangular wave at the output terminal. If you are going to give a sine wave to the differentiator circuit, you are going to get a inverted sine wave at the output terminal. This is how the differentiator circuit will give a various output waveforms. So is the differentiator clear to you? So if we'll just revise the things what we have seen in today's lecture, we'll go to our first slide and just compare. If you, why I have told you two circuits together, that is of integrator and differentiator, because the things are very common in both the applications, in differentiator and in integrator. The circuit is same, just you will have to replace or interchange the value of R and C over there. You have to start from op-amp as an integrator or op-amp as an differentiator only. This circuit we have just given. This slide is just an introduction for you to understand what is an integrator and how it looks like. But what is our basic circuit? Our basic circuit is how we can design an integrator by using a op-amp. So this will be your actual circuit where we have connected the capacitor and a resistance to the op-amp. Okay, so this is the basic circuit of op-amp as an integrator. This is the important one. Here you will know that we are having the output voltage as minus of Vc. So we have already deduced the equation for what is C, that is the voltage across capacitor. So we will write output as minus of 1 by C integration of Vi divided by R dt. This is the integrator circuit. That's why the equation will be as minus of 1 by C integration of Vi by R into dt. Okay, just remember this is the integrator circuit. Finally, op-amp as an integrator, this circuit, if you replace or if you interchange the value of capacitor and resistor, if you keep your capacitor over here and if you place a resistor over here, the circuit will be called as op-amp as a differentiator. Is it okay? So remember the two circuits, the difference between two circuits and the output voltage also. So it will be easier for you if you just have a comparison between the two circuits, so it will be easy for you to remember. This is the op-amp as an integrator. We have written the equation in terms of C and IC. So this equation will be finally what we will get at the output is minus of, if you take the integration from T to dt, you will have minus of 1 by RC integration of Vi into dt till the limits 0 to t. Is it okay? So this is how the output waveforms will look like if we'll give it to the integrator circuit. If you are going to give a square wave to this integrator circuit, what you will have at the output terminal? You will have a triangular wave at the output terminal. And these are the equations. These we have taken with sine and omega because we are having a sine wave. The time is with the time instantaneously omega is changing. Okay, that's why the equation will look like this. Now for today we have seen what is op-amp as a differentiator. So as you can see from this circuit, this is the same circuit, only the places of capacitor and resistors, they are interchanged and we are giving the input at this terminal to the inverting terminal. So this is also called as op-amp as an inverting amplifier and op-amp as a differentiator. So how we are going to have a general circuit for a differentiator, that is what we have seen. So this is a general circuit of a differentiator and the equation will be given as I is equal to C dVi by dt. So if we'll put this circuit to a op-amp, you will have a current to voltage converter also. That is what we needed. So here we are placing a capacitor in the input and at the feedback we have given a resistance. So this is basically called as op-amp as a differentiator. This is the final circuit of op-amp as a differentiator. In this circuit you can write I2 is equal to 0 minus V out divided by R. So you can write I2 is equal to minus of V out by R. This is how we have calculated the current, the second current which is flowing in this direction. Okay, So can we write it in the form of C into VI? Can we write current into form of C and input voltage? So this is written as C dVi by dt is equal to minus V out by R. So we can calculate V out or output voltage from the above equation, and we have written V out is equal to minus of RC dVi by dt. Okay, is this is the final equation for a op amp as a differentiator. Now we will have a waveform look. This is how the waveforms will look like at the input and output terminal of a differentiator. You can also give a DC voltage to the differentiator. These are very nice circuits to be taken in the practicals. If we'll be fortunate enough to have practicals this year, so in our labs we are going to see all these circuitry for your references. Okay, in your practical you have all these applications of op amp, starting from op amp as an inverting mode, as a non-inverting mode, integrator, differentiator, as an adder, subtractor. So it is very interesting to solve all these equations and to have to have a look at those equations to becoming true in front of your eyes. So just enjoy the circuits. We will have practicals soon. Just pray to God so that this pandemic year will be over. So this is all for today's class. If you have any questions, put it on the chat box, or you can message me also on the WhatsApp. Good. Thank you to you all for listening.